Hello. Today we're going over chapter 7 of chemistry, so let's get right into it. AICE only really defined 2 sections for this chapter, so that's all we'll be going over. We're going over equilibrium and some acids and bases, the general pH scale as well. So for the first section, we have some basic definitions that the AICE examiners might ask you. First is a reversible reaction. This is a reaction where you can reform the original reactant, so you can go from elements to a compound, but you can also decompose that compound back into reactants. That's generally this whole graph is where we're going from H2 and I2 into HI. So we see as we're consuming that H2 and I2, our HI is going back up, but at the same time, HI is going into H2 and I2. I know it's sort of weird to imagine, but it's almost like if you're in school and you're like walking in a hallway or going from class to class, there is going to be an exchange of students going into class as well as students going out of class. So they're both going towards different areas, but they're both constantly exchanging, if that makes sense. Then we have dynamic equilibrium, which is where it is the reversible reaction, but it's where specifically the products and also reactants reach that reach that part where they're not changing concentration anymore. We see that in the red part where the concentration is equal. We'll say this is the hallway metaphor, that at this point it's like maybe halfway towards class switch. So we have this equal amount of students in class, equal amount of students outside of class, and the concentration of them is the same. There are 4 qualifications for a dynamic equilibrium. It has to be a closed system, that way no matter is lost to your surroundings. For example, we're dealing with gases in this one, so we don't want those gases to escape at all, and also we don't want those products to generally interact with other kinds of atoms or elements that may be in air. For example, we don't want to interact with oxygen in a huge amount or carbon dioxide. That could mess up our reaction, cause different reactions to occur. That may not be reversible, so we might not be able to reach the same kind of equilibrium. So yeah, in general, it needs to be a closed system, maybe some kind of lid on the top of the reaction area. And also number 2, so it is dynamic. These molecules are constantly moving and reacting. That's why we have dynamic equilibrium. We're constantly moving, constantly reacting, but the concentration of these reactants is going to remain the same at equilibrium. So even though we still constantly move from left to right, it's still going to be the same general concentration. But absolutely, please note that these concentrations are not inherently equal because let's say that you have 3 red balls, 2 blue balls, like 3 yellow balls, and then you have orange balls on the other side. Because you have 3 red and 3 yellow, you might technically form more orange. For example, let's say we have 3 red, 3 yellow, and that turns into 1 red, 1 yellow, then 4 orange. While those concentrations will add up to the same amount, it's not necessarily an equal same amount. So we don't have the same amount of orange as the red and yellow because the red and yellow combine together to form it. In the same way that the hydrogen and iodine that we see are combined together to form 2 hydrogen iodide. So these concentrations that will form are not necessarily equal, but they are constant. They will stay the same, but they're not necessarily the same as the other concentration. And also the forward and reverse reactions occur at the same rate. So when we forward and reverse, forward just means a normal reaction we typically see where we go from reactants to products. A reverse reaction means going from products to reactants. Because this equilibrium is dynamic, it's going to be constantly moving, right? But because the concentrations are going to remain equal at equilibrium, they're constantly going to switch back and forth at the same rate. It's almost like I'm throwing a ball towards the other side of the room, but my friend is also throwing a ball at the other side of the room. So the concentration of the balls at each side of the room is not going to change. It's just going to be tossed around a little bit. It might be in a different place, but it's still inherently the same amounts of atoms and molecules being exchanged on each side. And also with this graph, it's important to note that the dashed line we see is the time to reach equilibrium. So it's where those lines flatten out. When they flatten out, that means they've reached equilibrium. The concentration is absolutely constant at that point. Alright, we have this Jello Principle. I'm not going to attempt to pronounce this guy's name. It's some kind of French name that I can't say. I say Chatelier. That's not how you say it, but his principle is that if a change is made to a system at dynamic equilibrium, so a system that has already reached equilibrium, or will assumingly go to reach equilibrium, the position of equilibrium moves to minimize this change. Now, it's a bit of a weird concept, but it will make more sense with a few examples. It essentially means that an equation is going to like the way things are in a certain way. So if a change happens, it might change what's happening in the reaction, but it will still try to adjust itself as much as possible to make it how it was before. So there are 4 ways we can apply this. There's concentration, pressure, temperature, and a catalyst, and we'll go through all of those. So I've made this wonderful, wonderful drawing to show you how concentration might change. Of course, this would be with an equation, but I'm just having a picture here, so represent a bit more. So we have this happy bucket of sand. The sand just sort of chilling in there. And we want that sand to be as level as possible. That's how gravity works, right? It just sort of makes it all equal. We can't have just a pile of sand like we might in Minecraft. It would just balance out. So with the top, not the top, but sort of the middle example, we have a situation where we add a lot of sand to the left. That's going to make the sand fall to the right, so therefore when we have more added to the left, it'll go more towards the right. For example, if we have our previous reaction of H2I2 that turns into 2HI, if we add more hydrogen and we add more iodine, that's going to make more of hydrogen iodide. That's pretty much how it goes. We add the sand onto one side and it's falling over into the other side and smoothing out. Then we have the other situation where we can take away sand from a side and the sand is naturally going to fall back into where that hole is and it's going to level out once more. This is a situation where we remove hydrogen and iodine from the reaction we have, and hydrogen iodide decomposes itself a little more to make that sand level back out again. And the same would happen if we had it on the other side as well. For example, if we added more sand on the right side, it would fall back down towards the left. If we had a hole on the right side, the sand would fall back towards where the hole is, just to fill it up. We want that sand to be equal and level. That's how the equation likes it. It wants to be level all the time. Then we have changes in pressure, and for this I want to make a quick note that pressure can be proportional to volume. Pressure is inversely proportional to volume, so if we have a bigger volume, pressure is going to be pretty low, but if we have a small volume, pressure is going to be pretty high, so that's why I have my pictures the way they are. We have the top example where we have a high area, so it's pretty much going to be a low kind of pressure that we have in it, and maybe we see one thing react with each other. Because remember, reactions are when atoms bounce with each other and have enough energy to successfully form what is going to be on the other side. For example, it's like meeting someone at a party and you go to talk to them, and if you have enough energy with each other, if you have enough good vibes, then you're going to maybe exchange each other's numbers or continue from there. But if you don't, you're just not going to do anything. And when we have more pressure and less volume, that's going to increase the amount of general collisions we have per second. So therefore, we're going to have more successful collisions per second, right? Because sometimes you can just meet someone at a party and you're just not really vibing with them. They don't really have the energy you want, so you just don't react, right? And on the bottom example, we have that situation where we have less volume, so we can increase our pressure. And we can see how all these gas molecules, we have some of them start reacting with each other. We have the same amount of purple and blue molecules, but because of the smaller area and increased pressure, now they're reacting more. They have more chances at collisions per second, so they have more chances at successful collisions per second. And you might generally notice me saying per second. AICE wants you to use that word, and you have to make sure you say per second for these kinds of collisions, because collisions is a very big number in general. It's a very vague idea, but when you say per second, you're giving more of a unit to it. It's also very important to note that pressure is only going to affect gases. So I have these gases floating around, but on the right side, we can see that if we decrease our volume and therefore increase our pressure, that liquid isn't really affected, solids aren't really affected, they're just sort of chilling in there, right? This is because liquids and solids have more of a definite volume. Even if water doesn't have a distinct, liquid in general, doesn't have a distinct shape to it, it still has that volume that is there, so it won't be necessarily squished around as much as the gas molecules would be. So in the end, this shows us that when we have an increase in pressure, the side with more gas molecules are going to collide more, right? We don't really care about liquids, we don't care about solids, it's only with the gas molecules. And when those gas molecules have more collisions per second, and successful collisions per second, that means we're going to form more of what's on the other side. So an increase of pressure is going to mean the side with less gas molecules is going to have more concentration. And if we had a decrease of pressure, it would mean the side with the gas molecules aren't going to collide as much, so the concentration is going to shift back over to them. Alright, then we have the changes in temperature. So there's 4 ways this could happen, but I promise the ways do make sense once you look at them. There's exothermic reactions, which is when we go from cold to hot. I should try to show at the top of the snowflake and then to the fire. We can see this through a negative enthalpy value. The way our numbers is set in math, you can have a negative x value, so it's sort of like exo negative enthalpy. I don't know if that really makes sense, but also exo, heat is exiting, so it's going from cold to hot because you would feel the hotness coming out of the reaction you have. And then endothermic is when heat is like entering, you know, that En right there. It's a positive value. There's something a student said in my class that's always stuck with me. It's that Indo-Indonesia positive. It doesn't make sense. But if you can remember Indo-Indonesia positive, maybe that'll work for you. But pretty much it goes from hot to cold. Heat is entering, so it's going from heat into something cold. So example, this would be like a cold pack or something you put in the freezer and it's just cold, right? So I'll start with the top left and go from there. We have this exothermic reaction that is having an increase in temperature. So this reaction needs it to be cold, right? Because we're going from something cold to something warm. So an increase in temperature, we're already going to be at this like sort of medium temperature. And the other side is now even hotter. I want you to imagine that you can go from a freezer into a very hot area, maybe like a desert. You're going from a freezer to a desert. And when the temperature increases, the freezer is going to be more room temperature. And the desert, oh my god, it's going to be even hotter. You can barely even stand in there. So we see that equilibrium is going to shift to where it's not insanely hot. So it's going to shift towards where that left side is again, where it's cold. And we can look at exothermic when the temperature decreases. So it's going from cold to hot. Well, now it's going to be super, super cold. And it's going to that sort of medium temperature, going from a freezer into a desert. And now it's going from like maybe like a super deep freezer, one that might be used in labs instead of like for food handling. And that would instead go into like maybe like a room temperature area. So when you think about where you want to be, you definitely want to go into that room temperature place. And when I would do these kinds of questions, I would write out, okay, exothermic, heat is exiting. I would go from cold to hot. Temperature is doing this. And I would try to write out what would happen. If it's going from insanely hot, no, it's like a medium temperature to insanely hot. If it's going from insanely cold to a medium temperature, that's the best way I do these kinds of problems. But also for endothermic, that is where we have heat going into cold. Heat is entering the system, you could say. So this is going from hot to cold, and this kind of reaction needs heat in order to occur, right? So if we're adding even more heat to the system, it's going to definitely want to shift to the right. We're adding more heat, so there's going to be more of a successful interaction between the molecules, I want to say, because when you add heat to the system, you're effectively giving the molecules more energy, because the molecules, they're in this closed system, right? So in a closed container, these molecules are going a lot more zoomy inside this container. So they're going to be bouncing with each other more, so they're going to be colliding more per second, and having more successful collisions per second. We see that wording sort of come back in here. Then we have endothermic for a temperature decrease. We go from hot to cold, same as usual. And then we're decreasing temperature on both ways, so we're going from this little room temperature to a very, very cold freezer. So of course you want to go back to room temperature in every case. So a general rule, if temperature is increasing, you're going back to the side that was cold previously, and if temperature is decreasing, you're going back to the side that was hot previously. And to get marks on this kind of question for the written responses, you have to mention it would shift this way in equilibrium because it's exothermic, because it's endothermic. You have to see what kind of reaction it is for a mark. And then we have the final one. If we have a change in our catalyst, like the concentration of how much we have of it. So essentially, a catalyst does not change equilibrium. Think of a catalyst as a fast forward button on your remote. If you have a TV show playing and you press the fast forward button, it's not going to change the TV show. It's just going to quicken it up. So that's why I have a graph of here, where we have our reactants, they're sort of chilling right there, and then the catalyst provides an alternate mechanism or alternate way of reaction that then lowers activation energy. So without a catalyst, we can see our EA uncat, which is our activation energy without a catalyst, it goes way up. So we need a lot of energy in order to do this. But with the catalyst, it's the purple line and it's a lot lower. And we're still getting the same products in the end. So a catalyst is going to increase the rate of a reaction, but not the concentrations of the reaction. Okay, AICE tables. Some people really hate them, but I promise they're really not too bad once you play around with them a little bit. So, AICE stands for Initial Change in Equilibrium. Or initial is given in the problem. And it'll typically give you a few numbers, then not give you all the numbers, because if you start with reactants, it's going to give you, oh, you have 1 mole of hydrogen ions, you have a half a mole of chloride ions. And you need to figure out for yourself that if you're starting with reactants, you're having no products. Think of like, oh, you're just grabbing some hydrogen, grabbing some chloride, and just bashing them together. You don't start with any hydrogen chloride. You start with, well, hydrogen and I guess I'll say chlorine to make more of a difference. You got hydrogen, you got chlorine, you bash them together. You don't have hydrogen chloride yet because the reaction hasn't occurred yet. This is our initial, this is sort of like 0 seconds into the lab kind of thing. So this is pretty much always going to be a case. I don't think they rarely give you the amount that's like 0. So pretty much if they don't say anything for initial, it's going to be 0 for that amount, most likely, most likely. Then we have the change. So they're going to give most likely at least one kind of change in the problem. For this one, they gave us that chlorine is going from 0.5 to 0.2. So we just subtract those. 0.5 minus 0.2 is going to equal 0.3. And we're subtracting it, so there's a little negative sign. But this kind of thing is going to change if we have coefficients. So, for example, I have a little thing down here of H2 plus I2 equals 2HI. That's a very common standard reaction. And the change is going to be the initial amount that you had minus the final, or like the equilibrium value, and that's going to equal the coefficient times x. So for this case, h would be 1x, I would be 2x, then hi would be 2x because we have 2hi in there. So let's say hi went from 0 to 10, so 2x equals 10, but for I, it would go down by 5, for h it would go down by 5. We see how those numbers interact with each other a little bit. So for 2x, we would have that the overall change is 10, but x itself would be a number like 5, which would be then applied to the other kinds of elements interacting here. But for this one, we don't have to worry about it because they're just all 1 in this kind of case. So you would then apply these changes to the other cases. Whatever you start out with, you're going to subtract numbers. So for example, if I have hydrogen and I have chlorine, I'm going to subtract how much I have of those in order to make hydrogen chloride. So if we start with reactants, your numbers of reactants are going to go down. And because your products start at 0, you can't get a negative amount of products. So you're going to add whatever your changes to those products. I have a graph all the way back here that can show us how our reactants, they may start out, let's say this goes 0 to 10, maybe that's a bit like 7 they start out with. They go down increasingly as the products will increase. So we see this relation of the reactants, what we start with, are going down and the products are going up. So they're starting from 0 and then increasing, right? Because these have reversible reactions, because there's dynamic equilibrium, you're not going to get that reactants go down to 0 most likely. It's going to have just some kind of number, maybe a small number, but you're still going to have some kind of reactant there. And not to mention, it is very, very possible for you to start with products and then go to reactants. That's not a problem at all. I just think 99% of the time you're going from reactants to products. And then our final step is E for the equilibrium. You just do your initial, and then incorporate your change into that. If it's a minus, then you subtract it. If it's a plus, then you add it. So, for example, hydrogen, 1 minus 0.3 is going to be 0.7. For hydrogen chlorine, hydrogen chloride is going to be 0 plus 0.3, which is going to be 0.3 moles in the end. Also, important note, you have to start with a consistent and general unit for these. For example, your AICE table is going to be either like all in moles or all in concentration, right? Because you just need to subtract from the same numbers, that way your units, you don't have to convert all the time. If they give you only moles and they give you decimeters in the problem, I'd recommend just using your mole values and then changing it to decimeters later on, because you don't know what exactly the problem wants until they ask you for something else. And you don't want to do like extra work before you have to do that. And the reason why I might give you concentration and stuff like that is because we have Kc and Kp expressions. Kc and Kp are just concentration and pressure. It's not really super complex. Really, these are the same exact equations, but just with different variables, right? For concentration, you have to show them in brackets, not in parentheses or anything like that. I don't know if you'll lose a mark over this, but I know these brackets specifically mean concentration, so I'd recommend doing it. And this is the case where we have, it's always like products over reactants. What you have, like the actual compound or the element, is going to be inside the brackets, and your coefficient is going to be the exponent for that corresponding compound or whatever. Pretty much, you would find values for your concentration, and then plug them in, and then raise it to the exponent, and blah blah blah. For example, let's say C had a concentration of 0.3, and it had a coefficient of 3. Then you put 0.3 to the third power times everything else divided by everything else, etc. And remember, the way you can get from moles to concentration is by dividing by decimeters cubed. But they might give you centimeters cubed in the problem. You cannot use that. You have to convert your centimeters into decimeters. And the way you would do this is by dividing by 1,000. Then on the right side with our pressure, you'll notice that's really similar, but for this one you have to write a P and then your compound and that kind of stuff. I'm not sure if you'll lose a mark over the P once again, but I'd recommend writing it because, I don't know, my chemistry teacher said you always have to write it, so that's just what I do. Though I'm pretty sure you can put these in parentheses if you'd like to. You don't have to leave just P and 2 for whatever that, if that confuses you. It's still products over reactants. And you might be saying, Jade, you start with moles and then you're trying to get the pressure. How do we do that? First, you have to do a mole fraction. This is where we're taking our moles at equilibrium and taking it over the total moles of the solution at equilibrium. Let's say this past example. So if I wanted to find the mole fraction for hydrogen, I would do 0.7, because that's the amount we have at equilibrium, over 0.7 plus 0.2 plus 0.3. So 0.7 over 1.2. And that's going to be our fraction. Essentially, the mole fraction is like a percentage of what you have at equilibrium. So all of your mole fractions should add up to 1 in the end. And your mole fractions absolutely should be decimals. They shouldn't be greater than 1. And then after we have our mole fraction, we're going to multiply by pressure. I would say this is always given to you in the problem, but remember, you have to use pascals, not kilopascals. If they give you kilopascals, you have to divide by 1,000, then boom, you're good. You can start using that. But if you use, because I'm trying to figure out how to word this. So if you use kilopascals instead of pascals, you might get some marks still, but you might just like miss 1 or 2 just because you didn't get the right numbers in the end because you raised by these big numbers by different exponents, you know? So I'd recommend always converting to pascals and then going through. Then we have the lovely Haber process. So both Haber and Bosch worked on this together a while ago, and essentially the whole process is that N2 plus H2 is going to equal NH3, of course, with a bit of balancing in there. So we're forming nitrogen and hydrogen and to make ammonia. And this reaction is generally exothermic, in case you wanted to know for when we have changes in equilibrium and all that kind of stuff. The conditions for this are high temperature, high pressure, and iron catalyst. I don't think you have to memorize these amounts or all the specific kind of stuff, but I think it's just general knowledge to like have handy, you know? And the purpose is just to make ammonia, and ammonia is used in fertilizers, so that's why we have a connection there. And I just want to establish that when pressure is increased or the temperature is decreased, the production of ammonia will increase. Because if pressure is increased, we're going to have more collisions with the gas molecules. The left side has more gas molecules, so we're going to make more of what's on the right side. And if the temperature is decreased, this is a exothermic reaction. Heat is exiting. We're going from cold to hot. So temperature is decreased. We're going from cold to hot previously, now very, very cold, and to room temperature. We're going to go to the room temperature, so it's going to shift to the right once more. You don't have to memorize how equilibrium will shift. I think generally it's a pretty, if you understand how equilibrium generally works, you can just figure it out, but I just wanted to list those there for you. Because we also have the contact process, which is where we take sulfur dioxide plus oxygen and make sulfur trioxide. Oh, there we go. I just fixed a bit of a balancing issue. There are 2's in front of both of the sulfur compounds. This reaction is exothermic, just like the last one. We generally use high temperature, low pressure, and vanadium pentoxide catalyst. And the purpose is like the same as the last one. The last one was to make ammonia. This one's to make sulfuric acid. And since we also have, this is an exothermic reaction, we have two gas molecules on the left and one on the right. But also, I wanted to generally mention that when you have gas molecules and you're doing equilibrium, you have to consider coefficients, which I just forgot for a second. So on the left side, we have 2 gas molecules of one thing, then 1 gas molecule of one thing. So 2 plus 1 is 3. Then on the right side, we have 2 gas molecules, like 2 moles of gas molecules. That's how you could word it. So since it's 3 versus 2, we're still going to have, if the pressures increase, we're going to have more reactions on the left side, leading to more concentration on the right side. And if temperature is decreased, it's exothermic, just like the last one. So we're going to have an equilibrium shift. Cool. And now we have our second section, which is our theories of acids and bases overall. So we have our general pH scale. You don't need to know like what translates into what. Like they'll never ask you what is 11. Like, it's just you know that above 7 is going to be basic, below 7 is going to be acidic, and 7 is neutral. So 7 can include water, but also things that are around 7, maybe like 5 or 6, 8 to 9. These kinds of compounds can't really be easily broken down in water, and we'll have more examples like later on, but it's important to note that when you have strong acids and strong bases, they're both easily broken down in water, while the ones that are like really close to 7, really close to being neutral, but aren't, are only just partially broken down in water. And also we have our bases, we have acids, but we also have substances that are amphoteric, which is that they can be a base or an acid in a reaction depending on what they're combined with. An example of this is that water is amphoteric. That's the most common example of it that we see. And then we have the acids and bases defined by AICE for us to memorize. There's hydrochloric acid, sulfuric acid, nitric acid. Those are all strong acids, while on the other hand, ethanoic acid and hydrogen sulfide are both weak acids. Generally, any organic acids, so ones that include like a bunch of carbon, all that kind of stuff, those are going to be some of your weaker acids. On the other hand, for the bases, we have sodium hydroxide, potassium hydroxide, and also for the weaker end, we have ammonia. Somewhat general trend, but isn't always true, is that bases are more likely to have that OH, and acids are more likely just to have hydrogen by itself, sort of. As I'm going to butcher this a lot, but the Bronson-Lowry theory of acids and bases says that acids and bases come in terms of proton transfer. So acids are giving away a proton, which is a hydrogen ion, and bases are going to accept a proton. And in addition, this is like sort of implied by it, that bases are going to donate OH minus, which is hydroxide, and acids are going to thus accept it. But it isn't necessarily said, but I feel like it's just nice knowledge to know. As, for example, just previously, we saw some of these bases have OH in them, so that's how you can sort of perhaps recognize a base right away, assuming it's not like ethanoic acid, where it has an OH, but it's an organic compound, therefore it's a weak acid. The way I remember if it gives away protons, accepts protons, etc., is I think if someone's basic, they're going to say the word like O a lot. There's going to be like O, like a very simple reaction. They're not really adding much to conversation. So because they're giving O, bases are the ones who are donating O's, letting go of them, and giving them to acids. So from there you might be able to figure out, oh, then acids are accepting the OH, that means acids are donating the proton, bases are accepting the proton, etc. And generally I think it's important to know that strong acids are pretty reactive in general because they have the H+, and those conduct electricity really well. Then we have our last section where we're going over all these kinds of graphs. So these are ones where you start out with a base, and we'll see the variations. So I'll go top left and eventually to bottom right. Top left, we have a very strong base, and we have a very strong acid that is given to that. So we start pretty high, then we have this very sharp decrease, and we're down near that low area. Pretty much with all these pH things, you're going to see like a very sharp decrease. Then we have, when you have a weak base but a strong acid, so we're going to see that we're sort of near 7, you're sort of close there, but you're still considered basic. You drop down, go to that low level. On the other hand, if we have a strong base and a weak acid, we're going to start at high. It's going to take a while before we drop off, but we're going to get near that 7 once again. We're still considered an acid, but it's going to be pretty close. Then our final one is when we have a weak acid, weak base. From what I've heard from my chemistry teacher, this one is probably not going to appear on the exam, but if it does, just know it's a bit wonky. We don't see a sharp decrease like any of the other ones. It's just sort of going, blah, 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 blah. That's pretty much, I think, the sound the graph would make if it made a sound. In addition, these are all starting out with a strong base, but they can also occur with a strong acid or anything like that. We can, instead of adding acid, we can just add a base, and it would pretty much just work the inverse way, where for the top left graph, we would start with a pretty low one, then we would go up to a really high one. It'd still be a very sudden kind of rise, and they generally follow the same kind of trends. So thank you for making this far and studying chemistry with me. I know it's a hard subject, but I really appreciate you staying here. Let me know down in the comments if you have any suggestions, where it'd be like going over some practice problems for this kind of chapter or going over other kinds of chapters. I really appreciate the feedback, and have a nice day.